Hello, everyone, and welcome to our March Parity and Friends. I'm very excited to see you all here. Thank you so much for joining. Before we start things off, I want to remind you all that we have Polkadot Decoded happening in May 20th. Our registrations are open, and more importantly, our call for votes are open, so you can help us curate the program. I'll just post the link here in the chat, so you can get involved. So definitely go there and tell us what you want to hear at the next Polkadot Decoded. Very exciting. Before we get off with the event, I'm guessing most of you are familiar with Crowdcast at the moment. We have the open troll box, so there for free chat. There will be time for questions at the end of each talk, so please use the Ask a Question function. It's just to the left of the troll box at the bottom of the screen. Submit your question in there, and then I'll ask the speakers the questions at the end of their talks. And then also we have 3 polls. So it would be great if you can take a second just to give us some feedback on the polls. We just want to hear about your experience, like how well you know Polkadot, how well you know Substrate. And if you've been here before, we want to know who's new and who's coming back. So let us know. So today we have Tomasz from Parity talking about the off-chain database. And then following that, we have Vinye and Peter from Equilibrium talking about their advanced use of off-chain workers. So we're talking off-chain workers today. So without further ado, I'm going to hand it over to Tomasz, and we'll see Vinye and Peter after that. Okay, take it away, Tomasz.
Thank you. Hi, everyone. Let me quickly share my screen. Okay, I think you should see my screen now. Does it work if I go full screen? I hope so.
Yes, it does.
Okay, so my name is Tomasz Tybinga. I'm a core developer at Parity. And today I would like to talk a little bit beyond off-chain workers. So I'm not going to be focusing on any specific off-chain worker features, or maybe it is a feature of off-chain workers, or it is related to off-chain workers, but I'm not going to talk about off-chain workers that much today. Yeah, so off-chain workers. Off-chain workers are this interesting part of your runtime, of your Substrate runtime, of your blockchain runtime, that can actually kind of go beyond this restricted sandbox that Substrate creates for your runtime. So off-chain workers are able to run additional commands and have access to additional features that are not necessarily possible for the runtime. And this opens up a lot of possibilities. And today I want to focus on one of the features that is kind of, you can think of it as just something that off-chain workers needs, but I want to lift it up today to a feature on its own, and that's off-chain database. So what is off-chain database? Off-chain database is a local key value database accessible by the off-chain workers. What I mean by local is that it's not part of the consensus. It's not the same thing as the state that you have in the blockchain, which is part of the consensus. It is something that is local to your node, to your instance of the node. Okay, so it's not shared between nodes. It's just something on your computer. It is also known as persistent local storage if you look at the SPIO crate. And what it gives us. So off-chain workers can use this database to store and read values that are related to their execution lifetime. There is an API in the package already mentioned, and the crate that I already mentioned, SPIO. You can go SPIO off-chain local storage get. Then you pass a key. A key is just arbitrary number of bytes, and you get a value back, which is also arbitrary bytes. So this is like very low-level API that we give you in this primitives. Writing to the off-chain database is quite similar. You also just pass the key, you pass the value as bytes. So if you have some other type, you have to encode it obviously the default choice is to scale encode it. There is this first argument, which is storage kind persistent, and I'm gonna tell a little bit more after that about it on the next slide. Sorry. So what do off-chain workers do with that database? So you can store some partial execution results of your off-chain workers in this database. You can use it to resume the state of the off-chain worker, but there is a bunch of gotchas that you have to be aware of. So first is the fork handling. So off-chain workers are only executed if the block that we are importing is the new best block. What it means, if you are fully synced with the chain and you import at block n, let's say, and you import block number n+1, then it's the new best block, and off-chain workers will run. And if you write anything to the off-chain database, it will end up in the database after this execution. If, however, we import a block which is n-1, and this may happen in case there is a fork, off-chain workers will not run, and also whatever this off-chain worker would write to the database would not end up in the database. There might be a situation where you execute a bunch of off-chain workers from a fork, and then you switch to a different fork, and the only data that you will see in the off-chain database will be coming from off-chain worker executions that are run for the new best block. So only if the number is actually better than the previous number. Also, you have to be aware that off-chain workers may be running concurrently, which means that the off-chain database has to handle concurrency as well. So whatever off-chain worker is writing to the database, it's immediately there. So there is no kind of buffering, and we don't wait for the off-chain worker execution to finish. When you call set, it ends up being written in the database, written and flushed to the database. So you have to be aware that if you have two off-chain workers running and they kind of modify the same off-chain database entry, they will compete for that resource, and there might be some races. Okay, so it's quite different than the storage that you might be used to from regular runtime execution. It has interesting consequences, though. So I showed you earlier the low-level API, which you can use. But we also provide a high-level API, which is hidden under storage value ref structure. So we say that we want a persistent storage value, and then we provide the key. In that example, in line 2, this is example OCW last send. And it gives you an API called mutate. And this API is able to read a value and then write the value back after modifying it. And the thing is that since we might have off-chain workers running concurrently, and they both try to mutate the same storage entry, only one of them will succeed. So what mutate API is doing, it's using compare and set under the hood. And it will only, if two off-chain workers run the same code, only one of them will actually end up writing to the database. And this is something that you can figure out from the results that you get from the mutate call. So in case we get OK and then a nested OK inside, this means that we were able to write to mutate that value. In case we get an OK and then an error inside, which is the case from line 14, then it means there was a conflict. Okay, so two off-chain workers try to modify the same entry, and we have to handle that somehow. Then there might be an error as well, and this is an error that we explicitly return from the mutate function in line 6. So in case you, for some reason, in the middle of mutating, you figure out that you don't want to do it, then you can also return an error and handle it later on. So the way to handle conflict is up to you. You might want your off-chain worker to retry. or you might simply quit because you are assuming that only one off-chain worker should go into like a critical section of your code and perform some side effect. So the off-chain database is not only accessible from off-chain workers, but you can also use RPC to read and write to the database. So there is an off-chain namespace in the RPC methods, and there are two methods. One is called local storage get, second one is called local storage set, and it operates on this like very low-level API where we just deal with robots. So it's up for the consumer of this API to figure out what the data is supposed to be under each key. So what is off-chain worker database useful for? Off-chain database useful for. So first, I already mentioned that, kind of showing the high-level API. Since we have concurrency in off-chain workers, we can use the off-chain database as a kind of immediate API with immediate effects. We can use it as a locking mechanism to prevent this concurrency. So in case we want to make sure that a side effect is performed exactly once, or rather at most once, we simply create a lock using this compare and set API or this mutate API that I showed that makes sure that only one off-chain worker is performing that side effect, for instance, an external API call. It can also be used as an off-chain worker opt-in mechanism. So right now, the only option that you have as a runtime developer, or rather as a node operator, you can either opt out of all off-chain workers from all palettes that you have in your runtime, or you can opt in to all off-chain workers in the runtime. There is no selective mechanism that allows you to run off-chain workers, but only off-chain workers from that particular palette. However, as a runtime developer, you can implement this kind of opt-in mechanism in using off-chain database. Another use case is credentials for external APIs or some authentication data. I have a few slides later on when I show examples. Then exposing the internal state of what the off-chain worker is doing to external clients, for instance, to a UI that you are building on top of that. And the last case, which is, I think, the most interesting, and I want to focus or kind of emphasize on this use case the most, is the off-chain indexing, and that's something that we have added recently. Okay, let me go to all of these cases right now and provide you some code samples. So for locks, we actually have a convenient high-level type as well, which is called storage lock. It's from, I think, frame support off-chain storage lock or something like that. And this is exactly the mechanism that I mentioned earlier. It's implemented on top of the mutate API. So we create a lock. This lock will actually have a deadline of 20 seconds, which means that it can be held at most for 20 seconds. If it's not released after 20 seconds, or rather it's auto-released after 20 seconds. So then we create this lock. We actually call lock methods on this object. We get a guard similar to how you have a mutex, for instance. And then this perform external call is guaranteed to be executed only by one off-chain worker. And when the guard is dropped, the lock is dropped as well. So another off-chain worker can go into this critical section. Actually, I realized I'm missing a key here, but there should be a key so that you can have more than one lock in your code, actually. So the opt-in mechanism that I've mentioned is as simple as just reading an entry from off-chain database. Okay, so for every palette, I can have a special key that, when set, will actually run the off-chain worker code. And if it's not set, then the off-chain worker will do nothing. So when the node operator opt in for all off-chain workers, there's still this mechanism of reading off-chain database values can still be used to filter out unwanted off-chain workers. Obviously, you may think this is sort of like a hack. We are working on a better support for filtering, but this is a workaround that you can use right now. And the thing is that it's taking quite a long time because it's not trivial. Like Substrate doesn't necessarily have the notion of palettes and there are runtimes that are not necessarily built on frames. So we need something that is kind of generic enough and not only frame specific. So how do I set this off-chain database value though? So you can either set it through RPC. So for instance, as a node operator, you first enable all off-chain workers, and then you opt in or opt out by setting this RPC, setting this off-chain database entries through RPC. Or if you are building a custom node binary, then you can have custom CLI flag that pretty much whenever it's enabled, it actually writes to the database, and then it enables your off-chain workers from a specific palette. Similarly with the credentials, this is exactly the same thing we can do. We create a simple storage value ref. We read, for instance, a GitHub access token. And then when we perform this external GitHub API call, we pass the token with it. Obviously, this is something that should be local to a single node. You don't want to have a GitHub access token stored on chain or being public. So this can be used to store this kind of safe data. Ideally, you would use a public-private key-based authentication and authorization, and we have a key store API for that. But for APIs that require an access token, that might be a workaround as well. External data for the clients, for instance, for the UI. So whenever your off-chain worker is doing something, for instance, here I'm performing an external call and then getting some response, I can write a storage entry for every execution of my off-chain worker and store the response that I got from the external API. Then my UI can simply query all of those entries over RPC and display what results the off-chain worker got from that API at particular block, at particular run. I can also store last request at key. So it's kind of a known key which contains a hash that I should query if I want to get the latest results. So this is something that goes into this kind of additional indexing. So a conscious design decision in Substrate was we are not the Substrate database doesn't store anything that is not strictly required for the node to store. So for instance, if you compare that to Ethereum, where every node is actually indexing all of the transactions that happen, and then you have this nice API where you give the transaction hash and you get the block number which contain that transaction. Then you have transaction receipts, so you know what happened in that particular transaction. In Substrate, we are not doing that because it turned out to be really not a good choice. Kind of, if you expand this over a long term, this indexing data tends to grow significantly, tends to slow down your node, and for many clients is actually not necessary to have at all. So instead, Substrate stores the minimal amount of data. So for instance, events, so the fact if a transaction was successful or not, is only part of the state. So you can, at each block, you can query the state and you can figure out which transaction failed, but there is no additional database. And you don't have this archive data unless you are running an archive node, obviously. So what we can do, what we can try to do, is to use this off-chain database as an indexing mechanism. So this is what was happening on the previous slide as well with this kind of off-chain worker stuff, but we can also expose on-chain data or kind of try to archive on-chain data to this off-chain database by copying it in the off-chain worker. So what we do here, we get the latest block number, we get all of the events that happened in the current block, we create a special key, which is events off and then the block number, and under in the off-chain database, we store the set of events there. So when someone opts in to run off-chain workers, despite not running an archive node, in the off-chain database, all of the events will be stored as well. However, you need to be aware of the gotchas that I've mentioned earlier. So off-chain workers are not guaranteed to be executed for every block. So we will only get events if the block is the new best block. So if we use this naive implementation, we might have gaps. We might have events coming from an incorrect fork in case we do a reorganization. And that's one of the cases that we wanted to support as well. And we were thinking how we can maybe make it better to expose or to persist the on-chain data or the data that was initially on-chain in the off-chain database. And this is the off-chain indexing API. So this off-chain indexing API is a way for the runtime to write directly to the off-chain DB. So all of the previous cases that I've mentioned, it was off-chain workers just using the off-chain database. Here, with indexing API, we have the runtime writing to the off-chain database. So what do I mean by that? So first, you have to opt in to this on your node. You have to enable off-chain indexing. It gives us predictable fork handling, because since it's the runtime writing to this off-chain database, then it means that any block that is imported, or rather every block that is imported, will be writing to this off-chain DB. So we don't run into this issue of, yeah, off-chain workers are not always running. For instance, they are not running if you are major syncing. Here, when we are major syncing, like every time we execute a block, it will be, and it uses some indexing APIs, it will end up in the off-chain database. Okay. Yeah, let me show an example. So I basically took the same example as earlier, but right now, look at line number 1. It's not implemented as an off-chain worker, but rather it's implemented as onFinalize in my runtime. So I take the parent hash, I create a key using the hash, and then I take the events, and I use SPIO off-chain index set, and then pass the key and the encoded events. Okay, so every time my block is executed, because onFinalize is executed at the very end of the block, every time my block is executed, the events will be copied over from the on-chain storage to off-chain database if the node operator opts into that. And what it gives us, this creates an additional indexing mechanism, right? Right now, I don't need to run the archive node, but my UI, for instance, is still able to query events from any point in time. So there is only set and clear API, obviously. The runtime has to stay deterministic, so it means it cannot read anything from the off-chain database. It can only append to this off-chain database. It's considered a side effect, so we don't even know in the runtime, we don't even know if it actually happened or not. We simply call the API and hope for the best, and it's up to the host environment, to the substrate configuration, to figure out if this should end up in the database or not. And yeah, we apply changes from all imported blocks. Note that this, however, doesn't solve the kind of canonicality of the data. So the thing is that in the off-chain worker, in the off-chain database, we might have data coming from multiple forks if my node imported different forks. The thing that would solve this issue is something that kind of goes back to maybe like the second or third slide that I showed, which is the storage kind persistent. There is another kind which is not implemented yet that is called local, and it should actually be called like fork local. And the idea is that then the off-chain database would only contain data from the blocks that ended up being canonical. So in case of the forks, we will to revert the data that turned out to be on a fork and not on the canonical chain. But this is something that still to be implemented. So yeah, two use cases. First, historical slashing. So we remove the old validator sets from on-chain storage in the palette session. However, in case of slashing, we need to know that the validator we are slashing was part of the set in the past. Okay, so we use the indexing API to store the old validator sets in the off-chain database, and then when the off-chain worker is reporting equivocation, it can actually use this off-chain database to generate a proof for the runtime that this validator was part of the set in the past. So this is purely to kind of save storage or on-chain storage. Another use case is the Merkle Mountain Range palette that landed in Substrate recently. It's an append-only Merkle tree like structure. And the idea is that on-chain, we store the minimal amount of data, but off-chain, we store all of the leaves. There is actually a custom RPC for MMR palette that is able to generate proof for arbitrary leaf, and this proof will be possible for this proof to be received by the runtime and verified there. Yeah, I got a little bit over time, so thank you.
Great. So we have two questions for you.
Cool.
The first one is, does it mean that in order to get data from some oracle like API 3 to runtime, it is required to fetch those data via off-chain worker, or I think wrong?
Yeah, so if you want to get data from Oracle to the runtime, it actually has to go through an extrinsic. So it can be either off-chain worker querying that data and then feeding it back to the runtime through an extrinsic. So this is something we can't really do much about. Like off-chain database is not really that useful here. The off-chain database and indexing API is for the reverse case, where we have some on-chain data that we want to kind of store off-chain for the off-chain workers, for instance, process later.
Great. And then the next question, could you explain more why there is no sure that on every block off-chain worker will be triggered / executed? Really no idea why is that?
Yeah, so the thing is that imagine you are syncing 5 million block network. You really don't want to run 5 million off-chain workers in case you are just major syncing. So the main use case for off-chain workers was if when your node is fully synced with the network, you can perform this additional services for the network. But when you are syncing, running this old off-chain workers is kind of useless. So they are meant for kind of real-time interaction. So this is why we don't run them when you are doing a major sync. Now, when you handle forks, or rather when there are forks in the network, we also consider, okay, either we can run an off-chain worker twice or like rerun the off-chain workers for the blocks that got reorganized. But then it means that you might be running, like in case of a long fork, this is sort of like a major sync. So you're now running old off-chain workers for some old blocks, and the data might not be relevant anymore. So the idea for off-chain workers was like, yeah, just let's just run them for the new data that we have and that we think is like the newest data in the network that we see, if that makes sense.
Cool. And then what is the status of the other off-chain worker storage kind that is fork aware?
Yeah, so we have, there is a PR, I believe it might have been merged like within the last month, that implements this kind of transactional storage that is required for this fork-aware off-chain database. So there is some work being done on that, but it's still not ready yet. And the main reason is just like shortage of resources and shortage of use cases. So if you have like, because most of the things that we are building into Substrate is based on the things that we require ourselves when we are building Polkadot. And so far we haven't been, like, we didn't have a compelling use case that required us to have this fork-aware storage. And also we didn't have, you know, enough push from the community to have that implemented. So if you have your use cases, then let us know them and let's talk.
Great. And the last question, are off-chain workers used for NFTs?
So the off-chain workers are actually, like, the main use case for off-chain workers was, let's simplify building oracles. So if the thing that you want to do with these NFTs is somehow related to oracles, like if you want to, you know, verify or fetch data that is related to an NFT locally, then maybe. But like, if you just think about NFTs as an ownership mechanism, then this is something that has to be done on chain. But like, some metadata might be done by off-chain workers. So some additional like extra stuff. Like I can imagine a UI which like queries, like NFTs are simply like contain some hashes of IPFS data. Then the off-chain worker is querying the data into the off-chain database, and then the UI is able to query that from the off-chain database, because like possibly the UI is not able to query it from the IPFS, let's say, because there's no gateway. But the off-chain worker can get the data locally, and then the UI can display this from the off-chain database. It's kind of a stretch, but yeah, that's how I imagine that.
Great. That's all the questions we have. Thank you so much, Tomasz.
Thank you.
Great. So up next, we have Finje and Peter from Equilibrium, and they're going to talk about their advanced use of off-chain workers. I'll let you both take it away from here.
Yeah. Hi, everyone. Just share, just a second, let me share my screen. Yeah, so can everyone see the presentation?
Yeah, but it's little one, I think.
Small?
Yeah.
Okay,
cool.
Is it good?
Yeah.
Okay, so a little bit of introduction. My name is Peter. I am the business analyst and the technical team manager with Equilibrium, and Venya, or in English, Benjamin, he is our tech team lead, and he will take a lead on the presentation, and he will share some technical specifics and about the off-chain workers, and later on I will talk about in greater detail how Equilibrium actually uses them and how we plan to use them. So without further ado, let's proceed to the next slide, and Ben, please go ahead.
Yeah. So off-chain worker consists of 3 parts: worker, storage, and indexing. You can read about it in Substrate official docs. In short words, worker is your custom logic code that is started after every block. If previous worker didn't have time to finish its work, then 2 workers will work in parallel. So worker have read access to runtime storage, and can set various types of calls or extrinsics to the runtime. Storage is just some key-value database. The worker has read and write access to it. It is different for each node, and you have read-write access via RPCs to it. And the last thing is indexing. So it allows you to get write access to off-chain storage from the runtime. So let's go to the next slide. So how can we use these features in our chain? Here are some use cases from the Substrate repo or different open source projects and some our ideas. The most common use case is oracles, judging to the open source projects and to Substrate repo. So you fetching some data from the outside world and maybe with some post-processing stored in your runtime storage. Additional actions for nodes is an interesting thing. So an interesting example in Substrate repo is I'm online palette. So there is no heavy computations or access to the outside world, but it keeps the system stable. So the main idea of this off-chain worker is to keep the system stable. The next thing is interesting thing is heavy computations. For example, off-chain election. We're delegating some additional hard work to validators to reduce the load to our runtime. And the last thing I think is additional storage. It's like idea because I couldn't find an existing example of it. It's something similar to liquid apps in EOS. So you can store some data in worker storage while store only hashes in runtime storage and reduce your runtime storage if you need this. So let's go next. Yeah, our oracles. So why using off-chain workers is really cool. Based on the example of our use case Oracle. There are two main cool features in our Oracle. First one, it's not about only our Oracle, it's this for all oracles in a Substrate framework. You don't need to install or configure some additional application. Every node has Oracle out of the box and you can launch it at every moment. Second thing, it is customizable. Nobody chooses for you which data source to use, how frequent each data. There is one Oracle to work with every data source. You only need to tell it how to parse the answer from API via RPC with help of worker storage. So the Oracle processor chooses where to get prices from, how to interpret them, how often to deliver new information, and this all about some several RPC requests to the node. We have Oracle as a product. So with help of off-chain workers, you can have additional products, not only inside your blockchain or runtime. You can create some other products. So go next. The second interesting thing is how we are delegating hard work to the off-chain workers. It is important that inside off-chain worker and later in runtime, we can verify, make sure that the request came directly from the validator and not from another node. Thus, we can add additional heavy actions to those who already have some trust, depending on our consensus. It is also important that these actions couldn't lead to some unpleasant consequences for the network, since the action is carried out without consensus on the part of the entire network. Here, one-way functions come to rescue us. There is some definition from the Wikipedia. One-way function is a function that is easy to compute on every input, but hard to invert given the output of random input. For example, it may be hashes or multiplication of two large primes by model of another prime. So we add heavy actions to our off-chain worker that is much cheaper in performance than runtime, but we can cheap test the result on chain. So we don't need to trust that this action is OK. We can verify this. Next, we have a few nodes that do some hard work. In the case of election, each node do this job differently. Due to the randomness with the method, we also do not want to do this work duplicated. We only want that each node do its own job. So performs only its own section of work. For example, when we have some work about accounts, each validator handles its own subset of accounts, like shown in this slide. But the situation may happen when a certain node stops doing its work. For example, some hardware issues or maybe something else. In order for this not to affect our network in any way, we add some small duplication of processing actions. So each validator checks only its own account and neighbor accounts for this account. But we don't want one client to be processed twice in runtime because it's additional load on our runtime, and we don't want this. So to do this, Substrate has a validate and cite method in which, using priority and provide stacks, you can set a priority. So processing validators accounts will have higher priority than neighbors and process only one request at once. So some theory about our off-chain workers. I told about this, and Peter can tell you about some concrete examples from our project.
Yes, thank you very much, Benjamin. So let's proceed. So indeed, we do use them in a lot of parts of our project, and here are some examples on this slide. Basically, if you're familiar with Equilibrium, you know that we are like a DeFi project, but unlike well, most prominent names like MakerDAO in Ethereum, we don't use aggregates, and we don't use like a single interest rate on every portfolio or every user collateral. That's why we have to calculate stuff per user or per borrower, because the borrower is a main like participant in our system. And this is one place where we use off-chain workers, because we need to calculate interest fees and charge borrowers with those interest fees when they are basically reach some threshold number. So this is one main use of the off-chain workers here. Another use, of course, is the Oracle that Ben has been talking about. And basically, we fetch some price data from the outside source and feed it to our blockchain. There's also the notion of margin calls. Basically, when borrowers in our system get under collateralized, we need to liquidate them. And on the past slide, Ben actually was talking about the mechanics of that liquidation, where each node has its own subset of accounts it monitors, and basically when it sees that someone needs to get liquidated, it sends an instruction to the runtime to actually liquidate or margin call a user. We also use off-chain workers for existential deposits. Basically, off-chain workers check that the account balance is greater than some predefined threshold, and if it's not the case, it also instructs the runtime to actually perform the deletion of that account. And within our system, we have like a notion of a master account and a sub accounts, and so we check that collectively for the master account and all of its related sub accounts. There are also bailsmen in our system, and those are like insurers who, unlike keepers who participate in auctions to liquidate back debt, they bring their liquidity in advance into the system. They earn interest on that liquidity, and they're basically take on liquidated debt and collateral of borrowers. And we need to calculate how much basically to give out to each bailsman. And we do that with the help of an off-chain workers as well. So we have temporary balances of our bailsman palette, and when those balances reach a predefined threshold, we basically do the redistribution in the blockchain. And the scheme related to this one is also the distribution of liquidity farming rewards. Basically, it happens via the same mechanism. So as you can imagine, we use off-chain workers throughout the system very extensively. And going further, there are other possible use cases we're definitely considering, and some of them are outlined on this slide. For example, as you may know, our ultimate product will be like a DEX, and thanks to Polkadot's interoperability, this DEX will combine lots of different assets, both crypto and derivatives on some traditional financial assets. So there needs to be an efficient way actually to organize this decentralized exchange. And one of the possible solutions, of course, is an off-chain worker where we can basically offload the matching engine and the order management and order matching to the off-chain worker, and only send instructions to the runtime or to the actual blockchain to perform actual transfers and settlements between user balances. There's also a notion of an off-chain as a product, and Ben briefly touched on that as well, where we've seen similar approach in EOS. That's where we are coming from, where the Liquid apps, they basically offered like, basically the same thing, an off-chain as a service for those people who run validators or nodes, where you basically configure something on your validator, and you start getting rewards from users from that, be that either an additional storage or an Oracle. If we look at our Oracle, we definitely have down the backlog or the pipeline, the modification of it, because we want to introduce the actual staking and slashing, where people who run nodes in our blockchain, they can opt into becoming an Oracle or a data feed provider, and they can earn some small amount of money for that. But staking and slashing, of course, is needed to penalize those who misbehave or who feed some prices which are way above or below some average or median price we're calculating. Also an off-chain storage, and the previous speaker, he was talking about that in greater detail, and indexing, yes. And also related to our decentralized exchange and API, where we want to provide users with some sort of API to handle order requests or order management and modification. And also another prominent use case for off-chain workers is some contingent orders and alerts, where you basically have some alerts set up in the off-chain where you monitor some thresholds or price levels or whatever, etc., etc. And this allows you to expand your order functionality beyond regular market and limit orders and introduce some different contingent orders like stop loss, trailings, icebergs, immediate or cancel, fill or kill, etc., etc. So as you can see, there's still lots of research going on internally with us and also in Parity related to this, the possible use cases of off-chain workers, and we're really excited about them. So I'm gonna hop off to the next slide. Well, that's it. And so the main takeaway, basically, we want you to have from our presentation here is that off-chain workers, they are not some additional logic which comes in parallel or is supplied in parallel to a validator or a node, but they rather play an integral role in the overall system stability, and they allow to introduce lots of cool different products and services and basically use an off-chain as a service, and that's what we are actually doing in our project. So that's it. If you guys have any questions, we'll be happy to answer those.
Yeah, we got one question for you. How do you ensure off-chain workers are not a weak point in a blockchain security?
So the main idea that's this some kind of one-way function. So off-chain worker is just check this guy for margin call or check this guy for existential deposit. It's not tell to the runtime to remove this guy or to margin call this. And then on-chain should check this and if some problems, for example, some validators starting to DDoS our system with wrong actions, with checking the guys that are not margin called, we can slash him or can remove him from our proof of authority system or something like this. So it's just few time and then slash and everything ok.
Great. So, and we just got another one. How are nodes incentivized not to turn off off-chain workers?
It's like off-chain like a product. So if you start this off-chain worker, then you gain some money. So for example, for oracles, if you don't want money, you can off your off-chain worker. So when we are talking about validators, so we are slashing them if they are turning off their off-chain workers. So it's part of our system, and if you want to be our validator, you should turn on off-chain workers in our system.
Great. So we have no more questions, but that was great. Thank you so much, Vinia and Peter.
Thank you.
Thank you so much for joining us today. It was great having you. Thank you to everybody who has joined us and watched us today. This video will be available directly after here on Crowdcast and also on the Parity YouTube. So if you want to go back and rewatch it, it's already available. Yeah, and our next event, meetup, will happen on April 29th, our next Parity Friends, where we'll have Darwinia join us. So super excited. A quick reminder about Polkadot Decoded. The vote is open. So help us curate the program. Tell us what you want to hear. And yeah, and then also the registration's opened. So sign up. So thank you, everyone. Have a great evening.
Thank you. Bye-bye.
Thank you. Bye-bye, guys. Have a nice evening.